Hello viewers, welcome back to the course on matrix computation and its application. So, in the previous lecture we have discussed many properties of the vector spaces. So, today we are starting with and continuing with the span of the set S. So, in the previous lecture we have just discussed something, the concept of span of S. So, in this we define the span of the set S. So, in the span of the set S, what we have a set of vectors. Suppose I take m number of vectors, and these vectors we are choosing from the vector space Vf. Then the set of all possible linear combinations of the vectors Vi's. So, all the linear combination we are taking here, and that is denoted by the span of S, and we also represent with the close bracket S. And what is that? It is a set of all the possible linear combination where alpha 1 V1, alpha 2, it is alpha 2 V2, alpha 3 V3 and alpha m Vm. So, this is we are defining where all alpha i's belongs to the field F. So, here we are taking all the linear combination, and after doing this one, what we found is that the span of S is a subspace of the vector space Vf, and it is the smaller subspace containing S. So, this one we want to discuss today. So, let us see what is we are going to discuss here is. So, it is given to me that S is a set which contains V1, V2, V3 and Vm, m number of elements, and this Vi's belongs to my vector space Vf. For example, if I take V3. So, in the V3 maybe I can choose my V1. So, V3 I am taking. So, this one I can write like here V3. So, this is I am defining, that is equivalent to R3. So, I am defining V1 a vector. So, this vector I can define as maybe 1, 2, 0. V2 I am defining as, suppose I define minus 1, 0, 2, something like this one. So, I just take two vectors and I take S as V1 and V2. So, these two vectors I am taking. Now, this is a set that belongs to my V3 or R3. So, this is a set I am taking. Now, what I want, so this is what I have defined that belongs to the vector field. Now, we know that the linear combination of vectors Vi's. So, this is equal to, I am defining alpha 1 V1, alpha 2 V2, alpha m Vm. So, this is the linear combination I am taking, okay, and where my alpha i's are coming from the field. So, that is a real number in this case. Now, what I do, I choose all the linear combination. So, I get a I will call it a span of S. So, this is a set which contain all this linear combination. So, maybe I can show by a graph, by a figure, that let V is my any vector space, and out of this I take a set S. So, this is my some set S. So, now I take all the linear combination and wherever it is falling, so this set will contain all the linear combination, and I represent that set by the close this bracket with the S, and I call this as a set made up of all the linear combinations of these vectors. Now, I want to check whether it is a subspace or not. So, this one I want to check. Now, we claim that this is a subspace of the vector space whatever we have discussing here Vf. It means that first I have some vector space V over the field F. Out of that I have taken a set S made up of some vectors, and then maybe I am getting some another set, I call it span S. So, span S is a subspace of V. So, this is what we are claiming here. Now, how we can do that? So, just what we are doing here is we have to satisfy the two properties of vector addition and scalar multiplication, and if that is there, then we can say that this is a subspace. So, we know that this is a subset of Vf, that is there, because whatever the set element the S is there, that is belongs to the V, and V is itself a vector space. So, all the linear combination will also belong to the vector space. So, it will be the set definitely. Now, let we take two elements. So, suppose I take one element, I call it U, and another element V belongs to span S, which implies that if this is belongs to the span S, it means it should be a linear combination of the vectors belongs to the set S. So, I am taking this one. V we are getting, suppose it is equal to beta 1 V 1, beta 2 V 2 and beta m V m, because it belongs to this one. So, definitely it will be of this type, where my alpha i's and beta i's that belongs to the field. Now, what about u plus v? So, u plus v, if I take the vector addition, then I can write this as a alpha 1 plus beta 1 v 1, because I can add component wise. I can write this as alpha 2 plus beta 2 v 2, alpha m plus beta m v m. So, this one is there. Now, you can see from here that alpha plus beta is a scalar, this is also a scalar, this is also a scalar, and then it became again the linear combination of the v 1 v 2 up to v m. So, now from here I can say that this belongs to again this set, because it is again the linear combination. So, again a linear combination of Vi's. So, it means it belongs to the set S. Now, so this is a vector addition. Now, we discuss the next property, scalar multiplication. So, I take any scalar alpha and I multiply to the set U. Okay. So, this is I can write as a alpha and U is already there. So, it is alpha 1 V 1 alpha 2 v 2 up to alpha m v m, and this is a scalar. So, I can multiply this as alpha 1 v 1 plus alpha 2 v 2 alpha m v m. So, I can write this one. Now, alpha into alpha i's, that is also belongs to the field F, because it is a scalar. So, from here this is again a linear combination. So, if it is again the linear combination, then I can write that this belongs to the span of S, and from here I can say that the span of S is also a subspace of vector space V with the field, because we know that if this first property and the second property, if the two properties are satisfied, then that all other properties will definitely be satisfied, because this set S is definitely lies in the vector space V. So, everything will be there, inverse will be there, additive inverse, additive identity, everything will be there. So, if we satisfy these two property, then we can, from here we can say that this is also a subspace of the vector space Vf. Now, the next thing comes is that how I can check that this is the, so because if you see from here, we have also claimed that this is the smallest subspace containing S. So, it means I have to show also that span of S is the smallest subspace containing S. So, this is my claim, or you can say it is a theorem, and then I can do a proof also. Now, I know that this S, so definitely the S, as we have taken in the previous, S is we have chosen like V 1, V 2 up to V m. So, this is we have taken. Now, if I take S is equal to this, where V I belongs to the vector space, and so this is we have taken. Now, I can write my V 1 as 1 V 1 plus 0 V 2 0 V m. Okay. It means V 1 is also a linear combination of these vectors. So, which implies it belongs to this one. So, the same thing I can do for all. So, I can write V m also 0 V 1 plus 0 V 2 up to 1 V m. So, that also belongs to span of S. So, from here I can say that S belongs or is a subset of this one. So, this one I can say. So, from here I can say that this S is contained in the span of S. Now, the claim is that it is the smallest subspace. So, smallest subspace means let T is a subspace of vector space V containing S. So, let I take the subspace T such that T is contained in S, that is S is containing in the subspace T. Now, we need to show that that this is also contained in T, a subset of T, okay, that is a subset of T. Or we can also say that this is belongs to T, this is also I can write. So, from here now, so this is how we can do that, because T is a subspace. Now, since S, the set S belongs to T and T is a subspace, which implies that linear combination, that a linear combination of elements of S is also belong to T. So, from here I can say that a linear combination of the element of S, that also is also a set is, or maybe I can belongs to capital T. Why? Because T is a subspace, and T is a subspace, we know that if I take any element of T, then their linear combination definitely will be in the T. Because what is the linear combination? Linear combination is basically, it is a two properties satisfying together, that is scalar multiplication and vector addition, and both are satisfied because it is a subspace. So, in this case any linear combination if I take of element of S, that will belong to T. So, if that is there, which implies that a element which implies that, and we know that linear combination of elements of S lie in this one, span of S, that if you take the linear combination, that will lie in the S. So, which implies that S will definitely also belong to T. So, it is also a subset of T, or maybe equal also. So, if I from here I can say that if the S belongs to there, then the span of S also belongs to the T, and definitely this is the smallest one, because I cannot find any other T, the subspace which will be contained in this one, because I have chosen the subspace which contain the S, and I found that the span of S is also contained in T. So, from here I can say that this is the smallest subspace contains S. So, S is always lying in the span of S. So, this is the way we can show that the span of S is the smallest subspace containing S. Now, After doing all these things, now we know that in a vector space I can have a large number of subspaces. So, I want to discuss what is going to happen if I add two subspaces. Like suppose I have a vector space Vf, and let in this I have this one subspace is there, another subspace is there, another subspace is there, another subspace is there, this is another subspace. So, I can have a large number of subspaces. So, I want to see what is going to happen if I add two subspaces. So, if U and W, if I take two subspaces U and W are the two subspaces of vector space V, then I want to discuss the sum of U and W. So, what is that? So, is defined to be the set of all possible sums of the vectors from U and from W, and it can be written as like this one: U plus W is equal to the element U taken from the U and small w taken from the this subspace W. So, I am taking one element from the U plus the another element from the W. Then we want to show that the sum is again a subspace of V. It means the summation is also subspace of V, and if SU and SW span U and W, then their union, so this is the union, spans U plus W. That is, if I take the union and then I will span, this is equal to this U plus W. So, this one we just want to discuss. Now, I want to show you that how it will look like. So, for example, now first I discussing U plus W. For example, so let us I show you with the example. For example, I just take a vector space V2, that is R2, and in this case I just take a U as x axis, means I am taking all the elements x 0 where x is the real number, and I take W is, suppose I take y axis. So, that will contain the element 0 y where y is a real number. So, these two subspaces I am taking, and it is a subspace because you can see that 0 0 is contained in U also and 0 0 contained in W also, okay, and all other satisfied. So, additive property, vector addition and scalar multiplications is satisfied. So, this is a subspaces of V2, that we know. Then I can define my U plus W as I am taking one element. So, that is the element I am taking x 0 plus 0 y, and if I add this together, then I will get x and y, where x and y belongs to the real line. Okay. So, in this case I am taking the linear combination this plus this and I am getting this value. Now, our claim is that this is also a subspace of V, okay, because a vector space is also a subspace of itself. So, no problem. And second one is that if I take the spanning set of U and spanning set of W, then their union I can take as a spanning set of U plus W. So, this one just we want to check. So, let us do this one. Now, the first property I want to prove, first one. Okay. So, first one is that the sum is again the subspace of V. So, this one I want to set. So, let I choose U and V belongs to U plus W, okay, which implies my U is coming from. So, I just choose two elements and then I want to see that I choose one element U and another element V from here. Okay. So, let us not taking this one, I will give some other notation. Okay. So, I just take some another notation. Let x and y, two elements I am taking, belongs to U plus W. Then x can be written as some U1 plus W1, where U1 belongs to U and W1 belongs to W. Similarly, y also U2 plus W2. Some element is coming from U and another element is coming from W, and this is also U2 belongs to U and W2 belongs to W. Then I just want to see what will happen with x plus y. So, x plus y can be written as U1 plus W1 and U2 plus W2. So, this one I also can write as U1 plus U2 W1 plus W2, because all these elements definitely coming from V and V is a vector space. So, I can do like this one, because in the vector spaces we know that associative property is satisfied. So, you can write down that, because U1, U2, W1, W2 all belongs to V and the associative property is satisfied. So, we know that we can add, we can shift the elements and can write like this one. Now, from here this U1 plus U2, that is coming from the U. So, and that is the subspace. So, this is also belongs to U. This is again the vector addition of two elements of W. So, this is also belongs to W. So, from here I can say that this is, from here I can say that x plus y also belongs to U plus W, because I am taking one element coming from U and another element coming from W. So, vector addition is satisfied. Okay. Now, another property. So, I want to see what about alpha x. So, alpha x can be written as alpha into x is U1 plus W1, and this one I can write as alpha U1 plus alpha W1, and this scalar multiplication is there. So, that is belongs to U, this scalar multiplication is there. So, that is belongs to W. So, from here I can say that the alpha x also belongs to U plus W. Okay. So, from here I can say that another scalar multiplication is also satisfying. So, from here I can say that U plus W is a subspace of vector space V, because both the properties, one and another property is satisfied. So, then from here I can say that this is a subspace of the vector space V. So, this is what we wanted to show. Now, this one, the second part is there. So, we will stop here and we will discuss this second part in the next lecture. So, today we have started with some property of the span of S, and then we have discussed that if we have subspaces, then how their combination, like summation, is whether it is a subspace or not. So, that we have discussed, and the other property we are going to discuss in the next lecture. So, thanks for watching, thanks very much.